I'm trying to make some people. I think I know about it. Because I know the first one I put I go in with it a lot. It was like N plus three N, so N. Yeah, I tried to say N cube, but no, it's adding, yeah. And then the second one, I think I did put. That's not important. It's hard, that's a. But we passed that matter.
All right. Thank you, everyone, for coming. I love the crowd that we're gonna have tonight. Before we begin, I just want to ask you all a question. How can you use data to make decisions? Like, do you have some information that you're trying to think of? For example, let's say, someone give me an example. What do you think is an example of data? Go ahead.
An example of data?
Example of data that you would use to make decisions with.
I don't know, there's like lots of examples you can think of. I guess like if you want to invest in stock, you could look at all the price ranges over time.
That's smart. That's smart. Maybe another one is trying to make a decision on, do you need to go to the grocery store right now? Already, here's a better one. Do you want to buy eggs right now? And the best data to look at that is the price of eggs, which is currently $8. So I don't completely recommend going to buy eggs. They're really expensive. But jokes aside, using data to make decisions is sometimes not easy, which is why tonight we're going to be covering Machine Learning 101, the what, how, and why of modern machine learning development. To give a short overview, tonight we are first going to be spending the first 50 minutes of giving a presentation on an introduction to what AI and machine learning is. Then we're going to take a 5-minute break so I can rest myself. And then for the last portion of the workshop, we will do a live coding workshop where I will show you how AI actually works in code and you can write your own AI. So first, what is artificial intelligence? From Wikipedia, they define artificial intelligence as the intelligence of machines as software, as opposed to the intelligence of humans and other animals. So basically, like instead of the intelligence we encompass, it's like what kind of intelligence can machines encompass? And it's a very broad field covering a lot of different aspects between machine learning engineers, cognitive scientists, neuroscientists. They all work in a field of artificial intelligence, and they're all trying to explore how machines can do intelligent tasks. And there's a lot of different AI techniques that have come out through the years. This is a near 100-year-old field, such as symbolic representation, rules-based systems, and machine learning. So that gets me to my next thing. What is machine learning? Because machine learning and artificial intelligence are not the same thing. They're used pretty interchangeably, but they're different. Machine learning is specifically a subset of artificial intelligence where the goal is to learn from data to improve performance. They're originally from like statistical models, which are near centuries old and are like an improvement and extension upon that. And the big thing about them compared to other techniques is that they learn about the data they're given on their own. And you may have heard of deep learning, which is a further subset of machine learning that is specifically focused on neural networks. But to get a better idea on what makes machine learning special, I'm going to talk about the old way things were done. And this was done up until late 80s, early 90s. And that was called symbolic representation. And the way that worked is basically humans would sit down and come up with a bunch of specially handcrafted features and rules that would tell the system, hey, here's how you need to think to get to your answer. And then you would input some information and it would come out to make a decision. Yeah.
What do you mean by black box?
So black box is basically a way of saying a model that we don't really know or understand the internals of. Like we know the code, but we don't fully understand the system by which it reached its decision.
Well, then how did they create it?
Great question. This is a slightly older slide. Most things would still be called black box. Back in the day, we would have understood these, like the symbolic representation, but what really fits the term black box is instead machine learning, which is the modern approach of things. This is where it actually gets to black box. So unlike the old system that used rules and an input that you make an output, modern machine learning instead takes the input and output you want and figures out the rules by which to get there. And so that was a complete transformation because it made it so that humans didn't have to sit down and figure out all the bajillion different rules and edge cases needed to solve a problem, but instead could let some algorithm figure it out all for them. So there's a bunch of types of machine learning. But for example, one of which is what is called supervised learning, which is basically there's an input and an expected output. That's the label. For example, here we have pictures of apples, and we're training the model to say, hey, these are apples. So when we input to the model, we want it to say, hey, is this an apple or not? And as you can see here, when given in, it can be an apple. And this is what is like commonly thought of machine learning. It's very broadly popular and like immediately understood. Another type is known as unsupervised learning. Unlike supervised learning, unsupervised doesn't have a label to go off of. Like there's no, if I give a picture of an apple, it can say it's an apple. It really doesn't know what these things are, so it instead has to learn patterns off of it. For example, here, it's learning to cluster all of these different groups here into their own like grouping. For example, like out of this just assortment of fruit, it's figured out that, oh, these are apples, oh, these are peaches, and oh, these are bananas. It really doesn't know that these are apples, peaches, and bananas. It just knows, hey, these things are similar to one another, so they should be grouped up together. And then finally, besides that, we also have reinforcement learning, which is what which you see a lot of in robotics, which is more of a agent environment interaction, where where something like a robot is going to try and do a task, it passes or fails, it adjusts itself, it learns to adjust itself to try and perform that task better, and it does that over and over and over and over again over a long sequence. Like how we learn, like we're going to keep trying to do something over and over and over again in that task. So those are the main types of machine learning. And tonight, we're going to be mainly covering supervised learning, and it's the easiest to understand and demonstrate, but unsupervised and reinforcement learning are still both very popular forms of machine learning as well. So with machine learning, actually before we begin, does anyone have any questions? No? Great. So with machine learning development, there's a sort of iterative process that goes by in development. And when every machine learning engineer does this, and when you complete this loop, you just do it over and over again to improve your model. So first is for a machine learning model, the first step is data ingest, which basically means to train a model, you need data somewhere. So you need to go get data. And that could be like, oh, you need to go collect your own data, go take pictures of cats and dogs out there in the world, or you can gather it from the internet. Like that's what OpenAI did from ChatGPT. They just scraped the entire internet of all their text information and trained ChatGPT off of that. So you just got to gather all the data you can for your task so that you can train a model. The next is data processing, which is where you take this raw data that you've looked at and you try and process it and analyze it into something useful. Because the biggest enemy that comes with machine learning is noisy data. This is the bane of existence. As you can see here, like let's just take a look at this little table here. We have age, where we have some people put in like just numbers, and some put in a date, and then someone said nothing at all, and then someone said like some people didn't fill out male or female, or gave an alternative option, or typed out the word, and then you have income, where some people have given nonsense option or specified the currency. You get the idea. when it comes to just raw data, people can format it in so many different ways. But you as a machine learning engineer have to clean it up, so it's all the same, so that your model can actually use it. And this takes a lot of time. For example, I spent the last 2 weeks at my job basically cleaning up data because someone else did it, and it became my problem. But this is the biggest thing of all. The other thing you have to do after you're cleaning your data is splitting it. So the question is, here's an idea. I want you all to answer me. Given that you have a whole bunch of data, how do you think data should be divided properly? Like, what would you think is a good way to divide this data up? You can just spitball me anything.
Per category? Category.
Yes, and I guess that is category. The way data is generally split for machine learning is that we split it up into approximately 3 sets, as we call them. The training set, the validation set, and the testing set. The training set is basically what is the data you're going to be learning off of. Is what it's like what I showed you before, the X and Y, to learn the rules. That's what this is used for. This is all the model. Your model is going to learn all the rules off of this data specifically. Then you test off of that with the validation set to see, hey, how well is your model working? Do you need to make any tweaks or modifications so that it can try and train off the training set better? And so you basically go through an iterative loop with these two, training and then validating your results over and over again until you get to somewhere where you're satisfied. And then you test on the testing set, which is separated from everything else, as you're really only supposed to run the testing set once. It's your final benchmark. Once you run it, you're supposed to be done and concluded. Because you don't want to go back and try and use the testing set to retrain, to change your model, because that is not a final benchmark. You just twisted your data around to try and fit another set better. So these are the main 3 sets. But a common technique that we will be covering tonight is known as k-fold cross-validation, which is very similar to like the traditional split, except instead of just taking one training split and one validation split, we do a bunch of them. We basically split up our training and validation data, put it together, and cut it into further chunks. And then we basically create a bunch of sets where some of the training, so where each set has some of the training data and then a different validation set. And so each set has a unique validation set about all these models go.
Why is it called k-fold cross?
Great question. It's called k-fold because the k-fold here is what each of these groupings are. Each of these is called a fold. And it's called cross-validation because you're having to create different crossovers. You're crossing over your training data, but with different validation data. So basically, we do this. Why did my thing turn off? I hate technology. Technology is evil, guys. Sorry, y'all. These USB ports here don't work. So whenever I have a bug, I have to exchange out the mouse with my clicker thing. I hate technology. There we go. Back to never. Okay. So basically, splitting this data into different folds allows us to basically evaluate our model on a bunch of different validation sets. So instead of just having one, where we can only get one conclusion off of our training, we now have, 4. We can now draw 4 conclusions off of it and aggregate them out together. So that was our model pre-processing and how we split our data. Once we have our data prepared and split and everything, and we really understand it, that's where we get to model training. And this is where we basically look at all of the many machine learning algorithms that have been created out there from the world and train them and see how well we do. And there are a ton of different machine learning algorithms. You got logistic regression, decision trees, report vector classifiers, k-nearest neighbors. This stuff came out in like the 70s, 80s, and a little bit into the 90s. Then you have random forest, boosting models, ensembling techniques, these came out a bit later. And then you even have deep learning and neural networks, which are all the rage today, as I'm sure many of you have heard. All of these are still used today. All of them have their own different uses and tasks. And it basically, in a good engineer, it's basically going to test a bunch of different techniques to see which one actually works best towards their data. So they're going to train off a bunch of different algorithms, but you have to have some way of testing them. You have to take some of that hidden data, you know, your validation, your testing set, and evaluate its performance. And the way we measure performance is with what is called a confusion matrix. And the confusion matrix is basically a way of seeing how your predictions match to your ground truth. And a good result would have like a lot of true positives and true negatives, and like very few false positives and false negatives. That basically means whenever things you predicted were positive, they were actually positive, and things that you predicted were negative were actually negative. You want that in your machine learning model. And then this also works if you're doing more than just like saying yes or no. It can work on multiple classes. But using this confusion matrix, you can use some metrics to actually evaluate your performance. And for classification, there's 3 common metrics you can use. One is known as the precision, which is basically a measurement of all the items that you thought were positive, how many were actually positive. So like I like to use a bag of marbles. If you grabbed a handful of marbles from a bag and said they were all red, how many of them are actually red and not like some other color? Another one is known as recall. And recall is basically the idea of all the things that are correct, are positive, how many did you get? Which, to use the bag of marbles examples, of all the red marbles did you grab? Of all the red marbles in the bag, how many of them did you grab? And then finally, we have accuracy, which I think is relatively understandable. It's basically a measure of how correct were you overall. It's like if you took a test, how many times were you actually correct versus all of the data. So this is commonly how models are measured, but there's many other metrics out there. There's like specification, there's R-squared, there's specificity. There's various other things. There's many different ways of measuring performance, but these are the most common techniques. And the biggest thing that we use these metrics for is to understand the biggest challenge in model training: fitting. Now, fitting is basically the idea of how well has your model learned to both the data it has seen and hasn't. And so the biggest only problem with this is known as overfitting, where if we look at the example here, we have a bunch of black dots that are, for example, our training set. We had a model learn to predict, make a model that could learn, hey, where would all these lines be? And it learned really, really well to fit onto this curve that the training point had. But then if we tested with like this star here and said, hey, is that the right spot? Like, hey, what do you think this value is? And it said, oh, it's all the way down here. Then it didn't do so well. It's gotten very good on the training data, but when it came to then testing it on data it's never seen, it just falls out completely. The other side of the issue is underfitting, where your model couldn't even learn to make a good understanding of what it was trained on. So like, as you can see here, there's not even a curved line for the training data here in the black dot. And so like it just poorly fits that, and then it's even also poorly fits to the testing data, which is even worse, because not only did your training fail, not even did your testing fail, the training failed. Whatever model you're using isn't working. But the goal you want to get is that having it just right, where not only does your model fit well to your training data, it also still performs well on your testing data. Does that make sense? Any questions? So once you train and test your model, and you do this a couple times, this is where you get to model deployment. And model deployment is basically where you say, great, I'm finally done training my model. I'm super happy with where it is. I got it all set up to be absolutely perfect. All the sets are doing absolutely great. Now let's release this to the world. And you can deploy a machine learning model many places. You can deploy it on the cloud. You can look at AWS or Azure or Google Cloud. I personally prefer Google Cloud a lot, but Azure is also great. Or you can deploy it to edge devices, like the smartphone, or you can run it locally. Or even better yet, some people run it on like embedded hardware, like people run it on Raspberry Pis or Arduinos. I know a lot of people who work on Arduino. That stuff is weird magic, even I don't understand how to get that. But deploying is, once you deploy your model out, comes the scariest challenge of all. Actual use case of your model. Now that you've trained your model on all the data you collected, it comes out for other people to use your model. And you have to hope and pray that all of your work has been enough for it to also work for them. If it doesn't work for them, you have to start this entire loop over again and figure out what did you miss before. So that is a high-level overview of the machine learning feedback loop. And even if your model is super successful, you're going to do this over and over and over again as more data comes in, either from you collecting it or getting it from other people's use cases. But you're always going to want to get more data, then you can get a better understanding of a problem and therefore make a better model. And does anyone have any questions on this before we continue on?
Yeah. How do you prevent that fear that you were talking about where it doesn't work for?
So I can't say you will ever solve the fear, but you can assuage it by being diligent across the entire pipeline steps beforehand. The way you can have confidence in your model is that you know that you got a good amount of data that encompasses your problem well. You cleaned it up so it works well for any machine learning model. You did a good exploration of your models and all your evaluations showed good performance on it so that, you know.
Oh, no, I had a question too.
So, yeah.
Okay, yeah, my question was, with the overfitting thing, like, how do you prevent that?
So for overfitting, there's a few different techniques. One is that you use a different machine learning. Overfitting, I mean, you can change, yes. Yes, actually, I'm not gonna go back on it. So there's a couple things. One is you do a different model. For example, a lot of people like to try and throw a neural network at some problems when a neural network is complete overkill, when something like a decision tree will work fine. The other thing though is what is called regularization, which is a technique we will cover, which I can cover a little bit later if people have any questions on that, which is basically a way of punishing the model to not overfit. It basically tells the model, hey, I see you're trying to get really fit onto this data and trend with these features. Don't. Stay generalized, keep your loss a little bit higher than what you could get to it, because even though your training is a little bit worse, your testing will be better. So the model we're going to be, yeah.
Well, are there like certain cases where like fitting it really closely to the test model is like better? I mean, like more general approach.
Repeat that.
Like, is there a case where like overfitting would be better, like fitting it to the test cases would be better than just having like a more general?
You mean fitting to the training case?
Yeah.
Believe it or not, I'm going to say, yes, there is a case, because I'm dealing with that case. The usual answer is no, but the honest answer is yes, it depends on your scenario. For example, I can give an example right now at my workplace. I have just a set of data or I need to train a machine learning model so I can understand what the model rules internally are that figure out how it can solve the task. And so I want that model to fit quite well to the data. I don't want it to overfit too much. There's always a too much to the point where you can't understand. But I'm just fitting the model to the training data and then testing it on the training data because it's that data I need to understand. So yes, there are cases where overfitting can be helpful, but it's a very situational thing. Normally, you don't want to overfit onto your training data. So tonight, our algorithm we're going to be covering is linear regression. This is the simplest model as we can get. How many of you remember linear regression from like statistics 1? Yeah, exactly. Congratulations. This is also machine learning. And so linear regression is, as you all already know, it really just comes down to a very simple mx plus b. You have your slope of your line and you have your y-intercept. And what we're going to do is to learn is that we're basically going to adjust these values with our training data until we fit well to our training data. And the way we do that is that we're going to make predictions on it, to make predictions using what our current M and B are, and compare that to the actual Y values and to try and find the error value in them. Like, yeah.
Is there like quadratic regression?
Yeah, the quadratic regression. There's a lot of different types of regression. You can do regression with any equation you want, as long as you have coefficients that you want to adjust to fit to your data better.
Yeah.
For example, you could do ax squared plus bx plus c. There you have three different coefficients you want to adjust. So the big thing about this is that we're trying to minimize the error, basically the difference between our predictions and the ground truth. And so in order to do that, we need what is an error measurement. And we're going to use the error measurement to adjust the weight, here are M and RB, to slowly using gradient descent. And there's a couple popular measurements for error that are used for like linear regression classification. One is the mean absolute error, which is just the absolute value of the difference between the ground truth and your prediction, which is shown with y hat. And then there's the mean squared error, which is mean of the difference between mean of the square of the ground truth value and the prediction. So we basically do a measurement of how wrong our model currently is, and then we adjust our weight slightly using something called gradient descent. And so this gradient descent is basically the idea of, let's say we have a landscape of our error. And our error is shown here on like this z-axis, and we have two parameters here we're adjusting. Here, this is like M, and this is B. And so all the different M and B values, we don't actually know this landscape. We just know what our current points are. And we know we're here, but we don't know the rest. And so we basically have our error landscape, and we're going to adjust our weights very slightly with a learning rate. But we know our error now, and we can say, okay, with that, we need to head that direction. We need to change our weights these directions. And then we do that by a slight amount with our learning rate, so that we can try and go down in error over time to some local minima. So that, and we want to reach a minima because that's the best we can do. And so we're basically going to make a prediction, find how wrong we are, and adjust slightly, and we'll adjust slightly, and adjust slightly, and adjust slightly, and adjust slightly, and adjust slightly, et cetera, until we reach a local minimum. Yeah.
Wait, what if the local minimum isn't like absolute minimum?
Great question. That is another constant fight in machine learning, is that the local minimum you may reach may not be the best minimum. And there's been a lot of work on that, especially in the field of neural networks, to try and make models that don't have a lot of possible local minima. But regularization also helps with that. If you regularize your model, that will help decrease the number of local minima that aren't the best. And there's also, just retraining your model creating a bunch of different versions of your model that you train different times to try and read different results. Because if you start someplace random and then you do gradient descent, maybe you'll reach here, or maybe you'll reach here, or maybe you'll reach here. If you train a bunch of different models a bunch of different times, you may find one that went really good that the other didn't find. So this is an overview of gradient descent. And if you want an idea of what that looks like, it looks like this. As you can see, the line is slowly beginning to adjust itself. It starts really, really wrong, and it knows it's wrong, so it adjusts its slope and intercept a little bit, and then adjusts and adjusts and adjusts and adjusts to fit the data as best as possible. And make the in front of it look like this. Yeah. So this is linear regression. And this is great. You can now fit a regression line. We can now have an X and a Y and fit a line to it. But how could we take this and classify data? Like, let's say you had an input feature, but then you had an output that's just 0 or 1. How would it be feasible to just fit a line onto that? Kind of, sort of. You can kind of fit a line onto it, but there's a structural equation out there that's really useful for this, known as the sigmoid curve, which, as you can see here, is basically a line that takes any value and fits it between 0 and 1. And logistic regression is basically linear regression, just logically disguised. As you can see here, we have a linear regression line, and it does fit to between 0 and 1. It does fit onto the data, but the line can go below 0 and above 1, which not the most useful for a model, may not train well, and linear regression may struggle with the fact that these are overlapping a little bit. But with logistic regression, with that curve, we can then instead say, okay, fit so that your curve looks like this. So that your curve will now adjust to be either between 0 and 1 at all times. And this is how we turn linear regression into a classification test. And logistic regression is designed to be a binary model. You basically either predict no or you predict yes, true or false, alive or dead, et cetera, uniform. And this is what the equation looks like. It basically takes the linear regression, which here like x, but it can be mx plus b, and it does a transformation of the odds of the answer, like the odds of it being yes versus the odds of being no. So when we train our model, we then have a model input that instead of x and the odds of y, the odds that it is yes or no, given the input and then the log of that. And so this is the base variable. Does this make sense to people?
Could you explain why we're using log? I seem like log based n or 2 is 1.
Yeah. So the reason why we're using log, it comes back to another statistical concept called log odds. How would I best explain log odds? Alejandro, are you familiar with log odds? I cannot give a good explanation on log odds. That comes down to older statistical theory, but I will provide a resource so that you can learn more about log odds after the workshop.
Okay, thanks.
But so this is logistic regression, and these are like very basic models. Like linear regression is a very basic model for doing regression, learning a line to fit data, and logistic regression is a modification of that to easily learn classification tasks. But there's problems with these linear types of models and results. And before, the biggest thing that you need to understand about all machine learning is correlation does not mean causation. Just because you see like a trend of, oh, hey, when this goes up, this also goes up, that does not mean that this going up causes this to go up. Like But they, you do get the idea, right? Oh, I know, no, like, there's an old website out there, that shows, false correlation. For example, the number of Nicolas Cage movies actually is strongly correlated with the number of shark attacks every year. Now, does anyone think that there's a causation between that? Do you think Nicolas Cage movies are causing more shark attacks? The answer is yes, of course. But no, the data can be correlated, but it can be for just random chance, or there's like a third variable between the two. They can just be careful making conclusions off of your model and its results. And then with linear models, they are limited. They are very basic models, and they don't really perform well on stuff that's non-continuous. If you have stuff that jumps around a lot, it's not good. And the biggest thing is that data can have like,
Let's go back to that question.
a lot of
No, you didn't.
That's in ChatGPT, but I get the idea of what it says. So, basically, when you're doing linear regression, you can just predict any number, like, like -0 to infinity. So a log function, the log probability will map it between 0 and 1. So if it's between 0 and 1, it'll be a probability between 0 and 100%. So it basically squishes the values. And that's like,
I thought that's what sigmoid does.
yeah, sigmoid like literally squishes them. I guess they like work together.
Okay.
Yeah, because you have log probability. This is the point that I wish I was like a math professor, but I'm not. But yeah, you should definitely look over the math. You can just get like a good intuition. But that's basically it. And so the probabilities make sense.
Okay. Okay, thank you.
Thank you, Alejandro. So yes, the other thing about linear models is that they really can't fit a non-linear data. To give an example, dot, 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 dot. You don't think I can fit a line to this? No. Congratulations, you found the first trivia, the most easiest case for linear models to fail at. This just doesn't work. Or better yet, if you were having logistic regression, dot, 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 like 1, 0. What would happen? So the linear models are not very powerful. They're very popular, especially in statistics and in the sciences, but there's a lot of more powerful models. But they're very popular because it's very easy to understand what a linear regression and a logistic regression model are doing, which I'll actually show you. So that's the biggest thing. While I'm going to be showing up linear regression tonight, there are much more powerful models that can learn a lot of non-continuous, non-linear patterns in your data. Any questions?
But yeah, so is it possible, so like with linear regression, right? Let's say you did have that parabola right there. Is it possible that it could find the M value to be like X, and then, like Y equals MX would be B would be like X times X, and it would be X squared plus B?
No, because X is a variable.
So it's just not,
X changes.
yeah,
X could be 1 or 2 or 3 or 4. X is the input feature
Yeah.
itself. M is just a constant.
okay.
So,
You'd have to change like the whole.
Yeah.
Yeah.
so cool. If no one has any questions, let's check out the notebook. We can finally get to the part everyone cares about. Can I lower this desk? I am too tall for this chair. I would recommend you work on this on your laptops. I have the QR code in case you want to scan on your phone, but I don't recommend it because it's on the code. There's also the tiny link. I can finally stop thinking about it.
We have to like make a copy of the notebook.
Yes, you will have to make a copy. I'll show how to do that. Change the display. Change. Sure. Sure. Yep. Great, cool. So welcome to our Jupyter Notebook tonight. If you are not familiar with Jupyter Notebooks, they are basically a way of running Python code. And I think other languages, I believe they have it for R as well, in small chunks. So like instead of having to run an entire file all at once, and if there's a problem with one line, you have to fix that one line and rerun the entire code, and you have to run it in chunks. So with this, the first thing we're going to be doing is we are going to be making a copy. This is the master copy and I'm not touching it, so we're going to just make a copy in Drive. So this is my own copy, and I want everyone to do the same, so you can make your own local copy. So before we can begin on programming, oh, let me zoom in for everyone first. Is that better? Can you see it now?
Oh, yeah.
Great. Let me also zoom in on my end. I have a little computer here to finish it. So before we begin, I want to talk a little bit about libraries. How many of you are familiar? How many of you are not familiar with Python's like library system? All right, one of you. So are you familiar with JavaScript in NPM?
No.
Okay. That's no worries. So basically Python is. So Python as a language is very powerful, but it was not originally made for machine learning by anything. It was made in the 90s for general programming. I don't really know the history of Python, and it's changed so much since it's come out. But the way Python, and actually JavaScript too, and a couple other languages work, is that to add more functionality to the languages, there are libraries out there that add new functions, such as like showing graphs, doing array manipulation, or doing machine learning. And those are what are called libraries. And they're like publicly available, and you can just install any of them that you want. If you want to look it up later for Python, it's called pip. Very useful, very powerful. But for machine learning, there's a couple different libraries there's a few different libraries that are very useful. The first one that you will use if you become a machine learning engineer for the rest of your life is NumPy. NumPy is a library that is basically Python's way of actually having arrays. Because Python only has like lists, which are funky in that they're like not arrays as you probably learned them in like intro to C, where like set size, you can't grow them or shrink them. Like you can grow and shrink lists as much as you want, but you can't really do a lot of easy math on it. Like if I wanted to multiply two arrays together, I would have to iterate through each value one at a time. And with Python, that's really slow. So NumPy allows you to do different manipulations of arrays really, really fast, because it basically is just running C underneath in Python. So it's like doesn't a snap, especially if you have an array of 1 billion length and you're trying to multiply it against another one. Python, that's way too slow. You got for loops. C, instant. The next one is pandas. And pandas, you can think of as an Excel spreadsheet, but in code. It has a lot of the similar functionalities as Excel, where it has like everything laid out in a tabular format. You can do different operations on like different columns and rows and all of that. It's often how data is organized for machine learning in Python, because you can provide very helpful descriptors like what each column is, get some summary statistics, things like that. Then the third library here is matplotlib. This is Python's biggest plotting and visualization library. If you want to make like a scatter plot or a bar chart or a line graph, matplotlib is what you use. It's very powerful, very customizable. A bit of pain in the neck to use, I will warn you. But it's very useful, and you can do a lot of different things. And if you want to give like a good visual understanding of your data and trends, matplotlib is what you use. Similar to matplotlib is Seaborn, which is another library that basically adds on to matplotlib and provides a lot of very helpful plotting convenience function. Because matplotlib provides a lot of basic plots, but it was more designed to allow you to build whatever plots you want, rather than providing you a bunch of pre-built plots that are really good. Yeah,
What did you say?
it's basically an Excel spreadsheet as a code. And so anything that you would do in Excel, in that sort of sense, like as in not coloring and all that, but like if there was anything fancy you want to do in Excel, like manipulating data, organizing it, transforming it all, Pandas would be that. So these are all great helper tools for doing machine learning, but one of the biggest libraries that you're going to be running into for machine learning that's not neural networks use something else, is scikit-learn, also called sklearn. This is a massive library. I mean, I've used it for the last 5 years, and I think I've only scraped the surface of what is all in this library. It basically contains as all the tools you could ever want for doing machine learning. Like, for example, here in model selection, we have splitting our data into training and testing sets, doing cross-validation, and then doing like grid search, which I will get to later on what that is. And then you could have like transform, like you have pre-processing tools, you have your models themselves, then you have a bunch of different metrics functions for measuring the performance of your model. For the beginning series of workshops, we're basically going to be in sklearn territory because it's just that useful. Even if you're not training a model in sklearn, you are probably going to be using all these like selection and pre-processing and metrics tools, because sklearn has just built them all out. But that's for the library. To run the code, the first thing you're going to do is press the button. It's probably going to take a little bit to start because words I can't speak. Because Google Colab, which this is what it is, this is Google's hosted Jupyter Notebooks, has to connect to a server before it can run. So that just finished running, as you can see by the green check mark. So now everything's been imported in. So the first thing we're going to talk about is regression, which, like you remember, it's just linear regression, it's just plotting an X and a Y. And this can be used in a lot of different things, stock pricing, housing, credit scores, etc. So to get an idea of what we're going to be working with regression, I first have a little bit of like pretend data here. And I want to first get a like visualization of what this looks like. Let's plot it out. So to do that, we're going to do plt.scatter or a scatter plot of X, Y, and let's do color equals black so we can just have it very, very stark. And then once you have that, you do plt.show. Oh, do I have Gemini on? I don't want to. 1 second, I want to print this off. And then to show our plot, we do plt.show. And then do the mouse thing. This is what it'll look like.
Wait, I have a question real quick. Is there like an input where we can label the X and Y?
Yes, so for that, if you want to do that, if you want to do that, you can do plt.axis, if I remember correctly. Let me make sure on that. Actually, no, it's X labeled. So the X label, and then we do X. Then PLT dot Y label. Y. This just names the X axis and the Y axis. And Z. Let me just do that slightly. Okay. Matplotlib likes to make giant plots, so I might be zooming in and out so you all can see everything. So that's a very basic plot. As you can see, it looks like our line is probably just a straight line, right? A little variation here and there, but I could probably get you all to walk up here and just draw a line up that, right? So what we want to do is you figure out a model that can do this. And so for that, we're going to be using linear regression, y equals mx plus b. But for that, we need to use gradient descent to adjust our model weights. And the way we do that is basically we're going to first, what we're going to do is we're going to just create, so actually no. So in order to do gradient descent, we need to know gradients. Gradients are derivatives. Whenever you're going to hear gradient descent, what you need to hear is derivative descent. Like remember the first derivative, the slope of a curve? Same thing, we're just learning the slope of the error curve. That error landscape I showed you before, how we were going down that. That's the curve. We're just learning to go down that. So that is generally done by calculating the derivative of our loss function, which is here mean squared error, by each variable. I don't want to look at that. You don't have to know all of the math here. I mean, you kind of should because this is calculus 1, but all you need to know here is basically this is what we're going to be implementing in code. But first, we need to set up an M and a B. Let's say M and B equals MP, dot random dot ran, which is an MP dot random. And this is just creating a random initial values of just random floats between 0 and 1. And then we also are going to want to set up a learning rate. And let's say this is 0.01. So we'll just run that little cell. And we can, oops. And let's just print out our M and P. So print F of M, full bracket M, B, full bracket B. Those are our first two random values. 0.79 and 0.85. Yeah.
What is the learning rate?
So the learning rate is basically how much we actually adjust the value by. I'll show it in a bit, but we don't want to just adjust the gradients directly. To give a good example why is, let's say this was our curve we were trying to learn on. And that is a terrible worker. I have a wonder selection of markers here though. Let's say we're trying to learn here. And we want to go down, obviously. That's what we're going to want to go down on. And let's say the gradient was massive. Instead of jumping to here, it can instead try to jump to here. And so that was a massive jump. It basically overshot the minima. And so let's say then it wanted to try and say, okay, we're going to adjust again. And instead of adjusting to here, instead adjusting. Okay, we're maybe getting good. But then let's say, great, I try again, and now it's jumped up. And adjusted itself so that it's now even higher. And then it just jumps up and up and up. So what's going on is if we just take the raw gradient, there's a high likelihood that we won't actually reach a minima, and we'll just bounce around the minima over and over and over, like, and never actually settle down. Because our gradients are just too high. So instead what we do is that we basically just, instead of taking the large step, we take a small step. So we multiplied it times our learning rate. And so we take a small step, and a small step, and a small step, and a small step, and a small step.
So where in the gradient descent equation there is like the learning rate effect?
So the learning rate is applied after we calculate the gradient, and I'll show you that in code.
Also, I think I kind of understand most of this, but what are the, is that like alpha? What is alpha L?
Oh. Oh,
What is that with respect to?
um,
Oh, is L loss, I assume?
you mean this?
Yeah.
That's the partial derivative symbol.
Okay.
Yeah, because normal derivative, like if you're just having this. That means there's just one,
Yeah.
there's just one variable. You're just deriving, it's like if you're only doing like mx. There's only one variable in the equation that you might want to be deriving by.
Yeah.
But when you have multiple variables, like you want to find out mx and b because the equation's reliant on both,
Yeah.
then this is where you do the partial derivative.
Oh, right, because if you treat B as a constant, then it'll just turn to zero.
Yeah.
Okay.
Yeah. Yeah, this is where calculus comes in. Pay attention to math. No, to just do, math is very important for machine learning. So there's a bunch of steps that we have for this. So first, in order to find an error, we need that predictions. We're going to do y pred equals m times x plus b. So to calculate that, we're going to need to calculate the error next, which is error is equal to np dot mean, numpy, and then the mean function of y, which is our ground truth, minus y prediction, which is our prediction. And then square is squared in. This is how, yeah, the double star is basically how Python squares things. So now that we have calculated our error, we need to take the gradients here and calculate them. And for that, you just need to follow me here of dm is equal to -2 times np dot mean of x times y minus our y prediction. And then similarly for db is -2 times np dot mean of y minus y prediction. And so this is, so these match our equation that we saw up here before. Like as you can see, the -2 times the mean, -2 times the mean, including the x. And then for a b is -2 times just the average of the difference. So that's calculating the gradients. And now when we want to adjust our weights, which is where the learning rate comes in. So we're going to do m equals minus learning rate times the m, and b minus equals learning rate times db. And then we can print out just the updated slope. Updated slope m is m, and then we just do a point for f to trim off the number of floating points we get. Updated intercept. B for f. And then we can also print out the error we got. Error. And then we can also just plot the data again. PLT scatter x, y, equals black. Label equals data. Let's say PLT plot x, y prediction. This will just plot us a line based off of our x and our y data, our y prediction. Color equals red. Label equals fine. And then we will just also generate a legend, so it's clear what's going on. And then PLT show. Now, how good do you think this initial prediction is going to be? You think it's going to be good, or you think it's going to be ass?
It's gonna be terrible.
Yeah, let's find out. Actually, it was pretty decent.
Yeah, yours wasn't that bad.
Yeah, it's random though, because everyone starts randomly,
Yeah.
so you don't know how it's gonna go. But this is not a great start, right? This is decent, but it's kind of not fitted that well. But let's run the cell again, because it just did one iteration of gradient descent, but we can do more. Let's run the cell again. Got a little better. The arrow went down and our line's looking a little better. Let's run it again. Even better. And run it again.
If we keep running it too much, would it overfit?
Technically, yes, here it would overfit, but there's no testing data here. We're just demonstration linear regression.
Okay.
We can run it again and again and again and again. Oh, it crashed. No, it didn't really crash, but like, you get the idea, yeah.
So the first time you ran it, you're using the first, like, random inputs?
Yeah.
And then like, after you keep, like, whenever you keep on running it, you just like update the new ones? right?
Yep. Yeah, so like, as you can see, the original values were like 0.79, 0.84.
In traditional programming, this would be in like a loop or something, right?
Yeah.
Yeah.
Yeah, we can program as a loop. I'm just showing here for visualization. Yeah.
Why- I got a question, like, why are we subtracting the derivative times the running rate?
Great question. So here's another fun thing about, so the reason why we're doing it is that we actually want to go down the gradient, and I'm back to the whiteboard. So when we normally calculate a gradient, let's say here, the way it's actually calculated, for example, if it was like y, x and y, the gradient function here, like if we calculate the gradient here, it's actually pointing upwards. But we don't want to go upwards, because this is like our loss curve. So this is actually our x and then our error. But we don't want to go up where it's an error. And so we now know which direction we need to go. We want to go in the opposite direction. So we go down there. But that's why we actually subtract. Because while we know the gradients and we know the gradients as they exist go upwards and we want to go downwards.
So then is there a gradient ascent where you go upwards?
There is.
There is?
Okay, and then why would you use it?
How you put it?
Okay, well, in any situation,
No, I mean, unless you wanna make it like,
well, okay.
I mean, there's cyclic learning rates and that sort of thing where you train really badly, I think, and you train to do it better. The answer is no, unless you're viewing it a weird circumstance. Yes, there's a gradient descent, a gradient ascent in the theoretical sense. In the machine learning sense, no, there is not a gradient ascent. You want to go down. Not-
maybe if we're getting 20 similarity scenarios,
Yeah, because you'd want the maximum amount of.
you want the most reward.
But then that's just but in that case, that's just an inverse. You have to
Oh.
inverse the equation so that it optimizes.
Yeah. Also.
I mean, technically that is gradient
Yeah,
descent into
exactly.
maximization, but we're not dealing with
Yeah,
reinforcement.
yeah, all right, now.
Yeah, and that's sort of a different flavor. That doesn't really, that does not deal with gradient descent in the to that sense. That's like Q learning, which is a completely different topic and its own bag of worms, so we'll not be covering that tonight. But yeah, so congratulations. As we saw from the initial value, yours are going to be whatever yours were. We got to much different values, right?
Another example for the grading ascent.
Okay.
So there's something called adversarial example, which is basically that you break the neural network to make a wrong prediction. So you can grab like an image simplification model. And if you have access to a model, you can see what the model will predict. So by looking at the gradient, you can add noise to the image, like.
Mhm.
Can you look up like adversarial?
Why would you do that? To make it more robust and to like get through the noise?
So. Yes, and no. Actually, yes, but basically add noise like that. You see a noise in the middle?
Yeah.
So you can trick the model to make a wrong prediction. So you could, number one, do this to make it more robust. Yes, good intuition. But also, if you're a bad actor, you could, like, I've seen people like, they like put like things like this on like stop signs. And they can break a Tesla to make a wrong prediction. Is it, and that's just like,
It's confused, yeah.
it's confused, yeah. And this is like a fundamental problem in AI that's still not solved, because you wanna get into something really, really hard and solve it.
Yeah. Isn't that fun?
So I see that in like the final prediction, it thinks it's a given and not a panda.
Yeah, exactly.
Yeah, okay, that's
So
like the
in
problem.
this case, you're doing gradient ascent, you're trying to. The
Unlearn.
opposite of what it was doing.
Yeah, you're trying to unlearn whatever habit it learned.
Yeah.
Oh, it's toxic.
It's toxic. Yeah, so. Great, so we fit a curve, right? Woo. But, and we can give like a final visualization of it, let's do just a final plotting, so we can do. Get that scatter. X, Y, color black. And then we can just do calculating our prediction. Complete. And PLT the plot, just to plot the line. We'll do this as my X, XC, so. Do that X label. X. PLT Y label. Y. And then we're gonna plot. So we'll call this our final function. This is it. This is the final line we have. This is exactly what we're thinking we're going with, is at the end. Great. But we need to measure the performance. We were measuring it earlier with the error, the mean squared error, but there are other metrics. For regression, the big thing we can use is R squared, which is also known as the goodness of fit. And to give a short explanation on what goodness of, like what R squared is, it basically is a measure of how much your line, like your prediction line, varies against the actual ground truth. And if your model fit perfectly towards your data, you would have an R squared of 1. And if you completely failed, like utterly, your R squared would be 0. So to show off this and the mean squared error, we can just use sklearn. I'm not going to make you all implement this yourself. So let's show off the mean squared error. And we can just show that off by calling mean squared error of Y and our Y prediction. And similarly, m equals R squared, goodness of fit, and R2 score, Y, and Y prediction. And I made a typo. So let's just run this. Ooh, 0.95, that's a great fit. We did really, really good. Can you all see this just to make sure? Do I need to zoom? Yeah.
Could you scroll up to the previous one, please?
This?
Yeah.
Yeah, absolutely. Don't worry, all of this code will be released after the workshop as well.
Thank
Yeah, I'm not gonna hide this from any of you. So, great. We've done regression and we trained it. Now, let's do something a little more real, a little bit more. Let's do classification. For tonight, we're going to be doing the wine quality data set. And it's it's a data set from 2009 that basically took in a bunch of different chemical and physical properties of wine and then gave a rating for them. I'm basically saying, like, hey, we got all of these chemical and physical differences. What do you think the quality of the wine is? 3 if it's absolutely dog shit, 8 if it's the best thing you've ever had.
Why did they use that rating scale 3 to 8?
I have no clue. Good question. I didn't read the paper.
Okay.
I don't question it. And so this was released for both red and white wines. I think tonight we're just working on the white data set. No, we're working on the red wine, but tonight I'm going to be going through that machine learning pipeline that I had talked about before. So first is that we need to do the data ingest. We need to get our data. So for that, we have so for that, we're going to be grabbing it from the internet. We have this URL for it, and we're going to grab that by doing pd pandas.read CSV. And then we're going to put in our URL, and then our delimiter equals. You give an idea of what a CSV file is. I know I just ripped off, I'll show back in a second. Basically, this is a CSV file. That's a horrible image. No, it's not. Basically, I do not want to put on that image. Open image on the tab. Basically, this is kind of the idea of what a CSV file is. It's basically just a bunch of data separated by commas. And this is a very simple way of storing like tabular data like you would have in Excel. But for ours, we're just going to read CSV and they're going to grab from the URL, but they use a semicolon. And we press that. And it read from the data. And just to make sure, we can do dia.info. And we now have a Pandas data frame, which is what Pandas is like table system is organized as. And we have nearly 1,600 entries with a bunch of different features and quality. So cool. We got our data. Hooray. So now that we've ingested our data, now here comes data processing. So now that we processed it, we need to have an idea of what we're working with. So to first do that, we need to set our data up to be useful for our task. So we're doing classification. So we're going to first do a transformation where we're going to take our data quality and make it either good wine or bad wine. And so for that, we're going to do df quality, which is basically we're just saying for the quality column, we're going to transform it as df.quality dot apply of lambda. We're going to apply a function to it of lambda x of 1 if x is greater than or equal to 6, else 0. And so this is basically just saying, hey, say it is good wine if the quality was greater than or equal to 6. Otherwise, say it was bad. And so we're going to run that. And so now that we have changed our data, we can show that off real quick. As you can see, it's either like 0 or 1.
So you did the DF
Mhm.
quality, like you're just making the table.
Yeah, I'm basically just indexing the table at that column. So like the data frame is basically, it looks like this. Like alcohol, sulfide. Quality, whatever. Everyone. The table. And basically by doing df quality. I'm basically just saying, hey, just focus on this for the moment. I'm changing values of this. Like if we're indexing into a array.
So why did we use that conditional if x is greater than or equal to 6?
Okay, so the reason why we're doing this is because the data set originally just has all of the qualities being arranged from 3 to 8. To simplify the task down to a binary of just like one class or the other, we're just doing a simple transformation.
Okay, yeah, but why specifically 6? Sorry.
Because it's 3 to 8, so it's like 3, 4, 5, 6, 7, 8.
Okay.
The balance of it.
Oh, okay, gotcha. Yeah.
Yeah.
So you're kind of splitting it.
Yeah, so now that we have our data, we're going to be, our next step is that we need to start splitting it. So for that, we first need to create an X and a Y. So I think, so for X, we're gonna just do quality, X is equals 1, so we have everything but the quality. And then we have Y, we can just grab quality. For training and testing, we can do X. Now that we have our our X and Y separated, we can split it up into our training and testing. For that, we're going to just do X train, X test, Y train, Y test. And split X, Y, and then we'll do a test size of 20% of our data, a random initial state of like 42, and stratify. Now, stratifying here, which is something I haven't covered before, is basically making sure to split our testing data so that the same ratios of the different values of Y are the same across the training and testing. So it's not like we suddenly split it so that all of the good wine is in the testing set and all the bad wines in the training set. Because you don't want that. You want it to be a good balance. And so let's print out the training and testing side. Training. Shape.
Wait, are they still data frames or are they something else now?
They are still data frames. All of this is still working on data frames. So now we have our training and our testing set.
What's the random state?
So the random state is basically an initialization, because so the splitting is randomized, but computers don't actually ever have true randomness. It's a pseudo random. And so we're basically just setting what the pseudo random seed is so that we can actually make sure our splits are always the same. So we all can get the same result here.
Can you explain again what the stratify was?
So basically stratify is making sure our split ratio is the same. I can give another example here. Let's say we had 60% of our data is red. And 20% is blue. When we split our data into training and testing, we want this to be the same of 60, actually this should be 40. Like 60, 40, 60, 40, and then 60, 40. And so that's what stratify do. It's just making sure the ratios stay the same as we split the data. Yeah,
This is a dumb question, but where'd you get the function train test split?
so, oh yeah, great question. Yeah, it comes from scikit-learn all the way up here.
Okay, sorry.
Yeah, no worries. Yeah, this isn't like, I gave everything that you need at the start. So if you ever are doing code, you can always just copy this for yourself. You're probably going to. So now that we've done our split, we can now get to exploratory data analysis, EDA. This is what 90% of your job will always be if you become a machine learning engineer, is exploring your data. Because you don't want to train a model without knowing what your data looks like, so you can know what model to use. So for that, we're going to be doing a few different things. First is we're going to be looking at a sample of our training data. So for that, we're just going to sample it by doing xtrain.head, and .head it basically just lets us peek at the first 5 rows of our data. These are the first 5 rows in X training, and they have these values. All look sensible to me, right? So once we can do that, we can also do some like summary statistics. And then do X train describe. And this just gives us some statistical information about it. Like we can see all the data we have, what the mean is, what the standard deviation, what like the quartiles look like, and we see we have pretty normal data, although some of these things have very high outliers. So this just gives us a good idea if there's anything wrong with our data or if there's anything weird. And then another thing we want to check for is missing values, because if we have missing values in our data, we need to either drop that entire entry, that entire example, or we need to fill it somehow. So with missing values in training data, then X train, that is null. And as we can see, we don't have any missing values. Great.
So what if we did?
So if we did, you could either just drop any rows, any like example that have missing data entirely, or you could fill them somehow. Like you could take of the column, if you have missing data for a particular feature, you could take like the average of the feature of all the examples that do have values and just fill that in for any of the missing data. Or you could fill it in with zeros or the mode. Basically, that's what you like use the statistics here for, is you would fill it out somehow. So we have some basic understanding, but now we're going to do a plot. Plots are great because they give a good example. So the first thing we're going to be doing is a correlation plot. So for that, so correlation, like I said before, basically the trend of one data point to another. If X is going up, does Y also happen to be going up? And we want to see this for our input features, because if two features are highly correlated, then we don't want to have both of them in it, because the model only really needs one then to learn the information. So first we're just going to set the size of our figure. So, and then to draw the correlation, we're going to do a heat map of xtrain.core for correlation. We're going to do annet equals true to plot the annotation. CMAC equals cool warm. This is just our colors. Format equals 0.2f. The rest, this is just how we print our numbers. Line width. And then mask equals tree u of xtrain. And this is basically just going to let us plot it as triangle. You don't need to do all, yeah.
So when you're selecting the X train, that's just the training set, right?
Yeah, that's just a training set.
So like what, so you select, for example, like X, the training set up correlation, that's selecting like specific like, values of it, or is it just like, just doing like the?
It's just calculating the correlation across all of the features. And I will show you what that looks like. So let me do feature correlation. 50 action. Yeah, give them- So basically what it's doing is by calling correlation, it just calculates the correlation between every feature against the other. For example, it's like, if you want to know the correlation between citric acid and fixed acidity is 0.68. And then I did give it as a triangle because when without it, you get, I can show you what it looks like without it. It looks like a full grid, but as you can see, it's just mirroring itself across the axis, which is not very useful. You don't need this upper half. It's just the same thing as the lower half. So for visualization, yeah, we just trim it off. So that's our correlation. Looking at our results here, we have a couple features that are pretty highly correlated with one another. Total sulfur dioxide and free are pretty high. pH and fixed acidity is kind of high. But usually you want to drop stuff if it's like 0.9 correlation. So we're not going to drop anything today.
So when I say, it has like the positive and negative, right?
Yeah.
Like, does it matter if it's like a positive, negative correlation? You're just looking at the actual value.
Yeah, you don't get that wrong. Positive basically means that if it's positive, that means that this one is going up. This other one's also going up.
Directly correlated with same.
Yeah, it's directly versus number, like, oh, it's negative, it's going the opposite way. It's still really the absolute value is more important because you want to know if two features are strongly correlated in either direction.
But in Ruby, I think it's features, you're kind of making it less redundant, right?
Yeah, exactly.
What's the benefit of that? Is that it just essentially?
Speed, and another thing is that if your model is filled with a bunch of highly correlated features, the model won't struggle to know which feature to care about. Like if you have 3 features that are highly correlated, the model now has to suddenly balance learning off of all 3. But if you drop 2 of them, then it can just learn really well off of the one. So it makes the model highly correlated features make it more difficult for the model to learn. But tonight we're pretty fine as it is. So the next thing we're going to look at are box plots. You all are familiar with box plots, right? So we're going to do a bunch of box plots for our data. So let's do another figure. And we're just going to set the size of it to 14 by 8. And so let's iterate through our features. So we're going to do for that for I, and then column, call in enumerate xtrain.columns. We're going to be doing multi.subplot 3, 4, n plus one.
Sorry, what is enumerate?
Enumerate basically goes, if you have like, a list of values, like 1, 2, 3, 4. Enumerate will just then, output like 0, 1, 0, 1, 2, 2, 3, 3, 4.
Oh,
It's a very helpful function in
wait,
Python.
so what is it? It turns them into ordinance?
No, like, let me go, like, how about A, B, C?
No, you also get the index.
Yeah, you basically just, you're pairing it with the index.
Oh, nice.
Yeah.
Okay, gotcha, nice.
Yeah. Very helpful. One of the most helpful little Python tools I learned, a couple years ago. So then we're going to do the box plot of our Y training data. And then a Y X train full. Q is Y train, and this is just how we organize the class file. Then legend equals false. Then POP title. Call person find. Whoops. Fine, loading. POP X label. Forwarding. 0 equals bad. 1 equals good. POP file label. However, then we're going to type layout just to make, just so it's easy to visualize. And then POP-show. And so when we run this, we basically get a bunch of box plots.
Just really quickly, like on the loop.
Yeah.
So you're saying for every like column inside the.
Yeah.
Like the main, it's like a matrix of.
Yeah, so to remind you what X-train looks like. This is what X-train looks like. We have a bunch of different columns up here, and so we're just iterating through all of the columns.
Every column you're getting like the values.
Yep, we're getting all the values for each feature, and then we're doing a box plot. So we can take a peek at our box plots. And the biggest thing I want to look for here is sort of how much our data is varying, how many outliers, and more importantly, how well is it separating stuff? And I see two big things here. One, alcohol, very good at splitting. Or at least it's at least some signal. Like bad alcohol has lower amount of alcohol, good alcohol has higher. Volatile acidity also seems to have some amount. Seems like for bad alcohol, it's slightly higher than good. Similarly for sulfates, it seems to have a bit of a trend, but a lot of the data doesn't seem to be great at splitting. So this tells me alcohol, volatile acidity, and sulfates might be useful. So now we have a
Mine looks very different from yours, and yes. I was just wondering what if I did anything cool.
Are you busy or video? Yeah.
What is the hue mean?
So Q is basically just how we're splitting the data into the good and bad quality. Q in Seaborn is basically coloring, but for here, Q is basically how we're saying, hey, plot the bad quality and the good quality. Just splitting up the plots. So don't forget,
It's okay, yeah, you're gonna post the code, right?
yes. Yeah, so another thing we can have is the pair plot, which it basically just shows a pair plot of all the values. So we can do that POT.pairplot, xtrain.join ytrain, and this is just joining our data for visibility. Then we can do equals quality. Do POT.subtitle. Pairplot. Features. Line quality. Y equals 1.02, just so we can set the title up top. And then we'll show it. No, this is gonna take a hot second to run, because we have a bunch of features. And this is what, so like, if you had 4 features, you have to make 16 plots.
If you put subtitle.
Subtitle just means super title.
Okay.
It's basically just another way of titling, and I'm just positioning it up slightly so it doesn't overlap on the plot. So this is gonna take a hot second. Take it, that's annoying.
What is the relevance of setting Y to 1.02?
It's basically just telling the plot how high I want the title.
Oh, okay.
It's visualization. Fun fact, if you become a machine learning engineer, the biggest thing you're probably gonna fight isn't your actual model code. It's going to be matplotlib. Because it is the pain. So this is a pair plot. And so this is sort of a plot to kind of look at the scatter plot and distribution of pairs of our data. And this is just another like useful way of trying to see how easy it is to split our data. I used this earlier this week because I was trying to figure out why some data at my workplace wasn't separating the way I knew it should. And the pair plot helped me realize I had mixed up my data. So looking at it, I see some interesting trends. Density and what is this, citric acid, that seems decently splittable. Citric acid and alcohol. This is a pretty busy plot, yeah.
Like, when I you say that, like, when you look at it, like, what makes you like know that? You know what I mean?
Oh, I don't know, I just think, this is my theories on it,
Like,
like,
so how did you
Yeah,
catch
yeah.
your,
How do you think of that? Yeah.
how did you catch your error at work?
Looking at that graph.
over my work, so basically. How about I tell the story afterwards? I don't, I can tell that story later. Whoa, why is everything zoomed in too much? Yeah. So like the reason why I'm thinking of this is like, I know, for example, free sulfur and alcohol. If we want to look at that plot, oh, that's right, I can just zoom in. I say that, I'm not 100% sure, but it does look like this line is kind of roughly splitting it. It ain't perfect, but there does seem to be some splittability. But this is my human evaluation of me thinking, hey, this data can be split. The model may just disagree with it. So that's the pair plot. Then we can also take a peek at our data distribution itself. We want to make sure we have the biggest thing we want to make sure of is that the different classes we have in our data are well balanced. Because if they aren't well balanced, then our model might overfit onto one class. Like if we had 9% red and 10% blue, the model might just learn to always say red, which great, it got 90% right, but it cannot work on blue at all. So we're going to do XY train. U is equal to Y train. Legend equal to false. And I'm going to move a little quickly because we're almost out of time. Yeah. Quality score. And as we can see, we have decent balances between the number of bad wines we have and good wines we have in our train set, which is good. So now that we've done our analysis, I think we can get, what? No worries. I'm just trying to go back because we're almost out of time. So now that we've trained it, we can now get to our training model, which we're going to use the logistic regression with the sigmoid curve we talked about before. So for that, we need to do we need to do some transformation of standard scaling, where we're basically going to take everything that kind of ranges from X to Y through Y, and turn it into 0 through 1. And this just makes it easier for the model to learn, and it's a very standard practice. Train, transform. Train, then X test, standard transform. But we want our data, our training and testing data to both be the same format. And so we just run that. Easy peasy. And so like we talked about before, we're going to be using cross-validation, which is a bunch of training and testing. So for that, we're going to first define our model, logistic regression. And we're going to set it to in a random initial state 542. And we're going to set it solver to Saga just so we can have some compatibility with some other stuff later down the line. So for cross validation, we're going to use CD scores. We'll cross.
Where's the solver?
What?
Solver.
Solver is basically it's basically the algorithm it uses internally to find to do the gradient descent.
Oh,
There's a bunch of different options that do have different backbones internally that can allow you to do different things. Saga just lets us do some other stuff. We're going to do cross-out score, train our model on our X and Y with 10 different folds, and we're going to score the fold based on accuracy. And so we can then print our cross-out scores, CP scores, and then print the mean score by MP that mean. CP scores. And so seeing our results, we have approximately 74% accuracy over our split. But as you can see, we have like 75%, 72%, 69, 77. With these different testing sets that we've created internally, we're getting a bunch of different varied results. So we can also then train on our entire training set to give another viewpoint. And then we can do a Y prediction of model.predict X test. And I know I'm really moving very fast. So now that we trained and done predictions, we can now do model testing where we're going to be looking at our confusion matrix and the different metrics we talked about before with the precision, accuracy, and recall. So first, we can print out our accuracy with our accuracy score of our Y test and our Y prediction. And we can print test accuracy of accuracy. And our testing accuracy is 74%, plus a little more, not great. We can then also do our confusion matrix of CM equals confusion matrix of Y test, and Y print. Then we can also do some visualization stuff of 6i equals 6/4, and that's not heat map, and equals trim, format equals 3, X tick, label. Classification report, classification report. Y test. Y prediction. Edit. And so, why are you yelling at me? Oh, excellent labels now. And so looking at this, our confusion matrix, we have a lot of correct answers for our bad and our good, but we got some things mixed up here. And we can also see for the precision and recall, we have very good recall precision for good wine, but not for bad wine. And then we have pretty good accuracy overall. Yeah,
So when like the false positives and the false negatives.
Yeah.
So like they just happen because like the model would like predict it and then you just double check it with the.
Yeah, yeah, I'm basically, the model made predictions, and I'm comparing it against what the actual answer is, and the model was wrong. It's basically just letting me know, hey, the model got these ones wrong and these ones right. So, great, we now know our model, and another thing that is super helpful to know is feature importance, which is basically our way of knowing what does the model think is important, which is super important nowadays because there's a big push on AI explainability. Like, you remember how I talked earlier about the black box stuff, how we don't know how models work? That's not acceptable anymore. We really need to know how these models work because everyone uses them. So there's been a lot of work on AI explainability. So here we're going to do that by looking at the importance of each feature to the model. So for that, we're going to just do the absolute value of the model and its coefficients. And then we're just going to do feature names, with x.columns. And then we're just going to bottom. We're going to do a bar plot of x equals feature importance. Y equals feature names. U equals feature names. And J equals bulk. Outlet equals, where it is. This is just another coloring. And then POT.title. Feature importance. POT.x label. Important. POT.y label. Feature name. And POT.show. So now we can take a peek at it. And this is what the model decided was important. And interestingly, it seems like I was right for my assessment earlier. Alcohol content would be important. The volatile acidity was important. So is sulfur dioxide and sulfates. Like the model is saying, hey, these are very helpful for me making my decision. Something like the pH level doesn't give a care. Doesn't care at all. So if someone was going to ask you, hey, what are the most important features for determining wine quality? You could say the data shows that alcohol content, the volatile acidity, and the total amount of sulfur dioxide are the most important things to make that decision. Yeah.
So when you say importance, it just means, it doesn't say which one's better, it just says what's.
Yeah.
Affecting the most.
It's like which weights are most influential.
Yeah, if they say what features are most influential on its decision.
So for example, when you say alcohol, like a change in alcohol would affect the.
Yeah. Yeah, the amount of alcohol does a lot of work in defining how good the wine quality is. So the value of it tells you what, if it's low wine, then if it's low alcohol content, then you're very confident it's bad wine. But if it's high alcohol content, you're very confident it's good wine.
So it does have less alcohol is worse, more alcohol is better.
Yeah, it basically you would have to look at the model actual values. Actually, I'm pretty sure I can just do that.
And then how do you differentiate correlation and causation?
Great question. This is where you have to be careful with your conclusion. Just because you see, hey, these are important, you have to go and do deeper investigation to understand, hey, why are these correlated? Why is it that these features are getting very important to the model making these decisions? And you have to come up with a reason. For example, why is good wine so much have more alcohol? Because people get drunk and you get on it. Who wants to drink low alcohol wine? And then sulfides, I think sulfides doesn't indicate that, but we are unfortunately out of time. There was a little bit I wanted to cover about hyperparameter. But that will be in the release code work. And if you have any questions about that, you can always just message me on the Discord server or message any of the coordinators or eBoard staff, and we'll be happy to help you. We want you to get into this stuff. This is our passion. So thank you everybody for coming. I really appreciate you sticking it out for 2 hours. I would really appreciate it if you could either this evening or tomorrow fill out this questionnaire form that we have. This is just going to let us know how we did tonight and what things we can do to get better. So, thank you, everybody. I hope you all have a good night. Don't get wet. I think it's raining outside. It was raining earlier. Go back for exams. I think midterms have started now. I know I have one today.
So is the next one on Wednesday? Is this weekly or
This is usually bi-weekly.
bi-weekly? Okay.
I'm a little too busy to do this weekly. And we need time to make sure all the materials are well prepared based on feedback.